Okay, we are moving on to section 3, that's solubility. When we're discussing solubility, we're discussing how well different compounds will dissolve in water. So when we're looking at solubility, we're looking at how much solute, which is what's being dissolved, how much solute can be added to the solvent, which is the base liquid. In our case today, we're mainly going to focus on water. Now, for a lot of things, temperature affects how much is going to be dissolved. And we're going to talk about that a little bit later. And the units that we talk about the solubility of is grams per 100 grams of water. Make sure you realize it's 100 grams of water. So if they give you a different volume or a different mass, you have to adjust it accordingly. Alright, so unsaturated solutions means that if you add just a little bit and it can still take more. So if you add a little bit of salt in here and yet you still want to add more and you're able to do that without it dropping to the bottom, that means that it is an unsaturated solution. So it's the amount you can add without it falling to the bottom. Kind of like if you think about Kool-Aid and you put too much sugar in Kool-Aid, there's a pool of sugar at the bottom of the container. Well, that's a saturated solution. However, if you are just starting to add it and you're able to add more, that's an unsaturated solution. So it contains less than the maximum, which means it can dissolve more. A saturated solution, however, already contains the maximum amount, and you're going to get this pool of solid at the bottom of it. It has undissolved solute at the bottom of the container. Now, it actually goes through an equilibrium process. That means that once it dissolves and sits at the bottom of the beaker, or the bottom of the container, bottle of the jug if you just make Kool-Aid or whatever, that's not the same sugar molecules the entire time. What's going to happen is some of them will dissolve, they'll get enough energy and dissolve, while others slow down and become a solid. And it's continually happening. It doesn't just sit there. That's why we have the arrows going back and forth. It both dissolves and recrystallizes, and that's called an equilibrium process. It's also called dynamic. So if you talk to somebody, you say that they're a dynamic person, that usually means that they're able to go to different conversations, be able to understand lots of different things. Their personality can adjust easily. Similar with the saturated solution, where the molecules end up going with the flow. Sometimes they turn crystals, sometimes they're dissolving, but they're constantly moving, they're constantly evolving or changing. So when we're trying to figure out if it's saturated or unsaturated, we're going to look about what's happening in the jar itself. So if salt disappears in the water, that means that there's nothing that's settling out and sitting on the bottom of it. That means it is unsaturated. Because in theory, I could put more in there if I wanted to. And then sugar added to a cup of water does not disappear. In other words, it sits at the bottom of the cup. Because of the fact that it's sitting at the bottom of the cup, that means that the rest of the water has as much sugar as it can possibly take, and the rest of them had to drop out, which means that's saturated. Remember earlier, and I said it had to be 100 grams, so grams of the solute per 100 grams of the solvent. Keep that in mind when we're answering these questions. So we're trying to figure out if these are saturated or unsaturated. Well, with A, 60 grams to 100 grams, well, 80 to 100 is the maximum solubility, so 60 is less than that, so that's going to be unsaturated. Part B, 200 grams of KBr added to 200 grams of water. Notice this is in 200 grams of water. Our amount is in 100 grams. It's twice as much. So we need to reduce that down to 100 grams by dividing it by 2. Well, if I divide that by 2, that means I also have to divide this by 2. And that becomes 100 grams of KBr, which is actually still over 80 grams. Since this is more, that means it's going to be saturated. And then finally, part C, 25 grams of potassium bromide with 50 grams of water. While the previous one had twice as much, this one actually has half as much. So we're going to multiply that by 2 to make it 100 grams, because it has to match this up here. So since we multiplied the water by 2, that means we have to multiply this by 2. So now we're talking 50 grams per 100 grams. Well, 80 is the maximum, so it's less than 80. Which means it's unsaturated. Now that was specifically for KBr. Every compound has a different solubility. It's called a solubility curve. And so if we're looking at this, like sodium nitrate is right here. That's how much it increases with temperature. So as it gets warmer, it increases how much it can dissolve. Whereas if we look at sodium chloride, okay, yeah, it increases, but not very much. It's a very small amount if you look at that. Ki, potassium iodide, increases quite a bit when the temperature increases. Notice that the highest temperature is 100 degrees. That's because we're talking about specifically water. And water boils at 100 degrees, which means that to be in liquid water, it would have to be between 0 and 100 degrees. If it's below 0, it's a solid. If it's above 100, it's a gas. So that's why it's within that range. So solubility depends on temperature. Most of the time, it increases with increasing temperature. Now that's only solids. Gases, however, decrease as the temperature increases. The molecules are moving faster and faster and faster. And since it's a gas, it tends to want to escape because they already have a lot of energy in them. And that's, well, so let's think about this in realistic terms. If you had a carbonated drink and you left it in your car in the summertime, sometimes I've seen people who have opened the door and the can fell out, and as soon as it hit the ground, it exploded. Or it expanded while it's in the car. That's because as it got hot, as the temperature went up, the gas molecules started going faster. And so when that happened, they tried to escape. And when they tried to escape, it exploded. Or if you think about fish, fortunately sometimes fish die in the summertime because it gets too hot. The reason for this is because we have air, we have oxygen in the water, and then as it gets hot, because when temperature goes up, the gas solubility decreases, the oxygen leaves, which means that there's less oxygen for these fish. So let's talk about Henry's Law. Let's go back to that Coke bottle thing. And I'm actually going to talk about a 2-liter pop bottle. You may notice that when you open a 2-liter pop bottle, or any can for that matter, it fizzes when you open it. And then you think to yourself, well, I'll just tighten the lid on tight and the carbonation will go back in. The problem with that is that these cans and bottles are under pressure. There's a whole bunch of gas molecules right above the liquid. And it's pushing it, and it's putting pressure on it, and it's pushing those molecules back into it. Well, once that pressure is released, all these molecules that were under a whole bunch of pressure now have a place to escape to. There's no way to get that gas back into it unless you put it under extreme pressure and add more molecules and push them back in. And that's what Henry's law is stating. It's saying that the gas in a liquid directly above it is the same pressure as the gas in the liquid. So as the pressure increases, the molecules are pushed back in and more gas molecules dissolve. That's all Henry's law is saying. We're going to switch gears a little bit, and we're going to talk about situations in which salts don't dissolve. We spent all this time discussing the solubility of salts. Well, not everything is soluble. Otherwise, we wouldn't have compounds. This is a list of solubility rules. So this is telling you when things do and don't dissolve. For instance, typically, chlorine, Cl-, NaCl is an example of that. Sodium chloride, that's salt. We know that salt usually dissolves in water, table salt. However, if it's mixed with, let's say, lead or silver, it's going to form a solid. And that's because the attraction between those two compounds are so great they don't want to separate. Another example, let's say we have hydroxide. Typically, hydroxides don't dissolve. They usually are solid. However, if you have it as sodium hydroxide or potassium hydroxide, then it will dissolve. And that's essentially how you use the chart. You match up the pluses and minuses on either side. So these are if they dissolve, these if they don't, and these are the exceptions. These are linking the two. So let's take a stab at it. Well, let's talk about barium sulfate real fast. Barium sulfate actually has a medical purpose to it. It's to enhance x-rays so we can look to see if there's an ulcer or something along those lines in the digestive system. Well, if we look on the solubility chart, sulfates are supposed to be soluble. However, when mixed with barium, they're not soluble. So because these aren't soluble, it's able to embed itself into the digestive tract, and you're able to see it. You'll be able to see issues. So let's take those rules and let's try to make sure they make sense. Potassium sulfide. Well, here's potassium. It's usually soluble, and it said it was sulfide. So here's sulfide. These are usually insoluble, but are soluble with potassium. So that means those are soluble. Let's skip down to this one because this is a typo here. Lead chloride, lead 2 chloride. Well, here's lead. They're typically insoluble. However, if we have chlorine, they're not soluble with lead. So that means that's going to be insoluble. Sodium hydroxide. Okay, here's sodium. They're typically soluble, but and here's hydroxide. It's typically insoluble. So here's our two ions are insoluble, but are soluble with sodium. So therefore, that means that that's going to be insoluble. Or, I'm sorry, that's going to be soluble. And aluminum phosphate. Here's phosphate. And there's no aluminum over here. Because I don't see an aluminum to be paired with to make an exception, I'm going to say that it's insoluble. And there you go. It's just a matter of reading the chart and seeing connections. So what ions each of these compounds insoluble in water? So what ions make these insoluble in water? So CDS. We're looking for either CD or S on the chart. S is right here. It's insoluble. That's the reason why it's insoluble. Fe or S. Well, we just found out that S was insoluble, so that means that S is insoluble. Lead to iodide. Well, here's iodine and here's lead. Iodine's usually soluble. However, lead are not soluble with these three. So that means that's why it's insoluble. And then nickel hydroxide. There's no nickel on this side. But here's our hydroxide. And that's what's making it insoluble. And that's the end of that section. And I hope you understand the solubility rules.